Hello students, welcome to the lecture series on digital electronics. It is a subject in third semester, Diploma ETCE. The course code is ETCE/DE/S3. I am Paulo Sridhar, course coordinator and assistant professor of Department of ECE, Guru Nanak Institute of Technology. So, welcome back to today's lecture number 13, which is the lecture of unit number 2. We are starting with unit number 2, that is Boolean algebra. So before starting the Boolean algebra, let us have a quick recap of the previous lectures. In the previous lectures, we had some syllabus overview and the course objective overviews. Then we had the differences between the digital system and the analog systems and the advantages of the digital systems over the analog systems, and all the digital logics, what is the logic and what are the advantages of the digital logic. Next was what are the applications of the digital system in the field of electronics, and all the various applications in other subjects like communication and signal system. That is how digital can be used in all the other subjects. Next, we learned about the number systems, that is the decimal number system, binary number system, hexadecimal number system, octal number systems, and also the conversion of one number systems to another. And binary arithmetic, that is the binary addition, binary subtraction, multiplication, the division, and all the examples related to them. How to represent the sign numbers, that is how to represent the negative numbers and the 9s and the 10s complements. Next, we studied about the logic gates. First of all, we studied about the basic gates, that is the AND, OR, and NOT gates, the truth tables, the logic diagrams, the logic circuits, the applications, and the TTL logic ICs that are associated with all the basic gates. Next, after the basic gates, we studied about the universal gates, that is the NAND and the NOR. Similarly, in NAND and NOR, we studied about the truth tables, the Boolean expressions, the logic diagrams, the applications, and the TTL logic ICs. After the universal gates, we studied about the exclusive gates. The exclusive gates are the XOR gates and the XNOR gates. They have got huge applications both in digital electronics. So, these two gates can be used as inverters, as parity generators, as parity checkers, as comparators, as equality and inequality detectors. And we have studied about all the applications and also the CMOS and the TTL logic ICs that are associated with the 2-input XOR and the 2-input XNOR ICs. After this studying about the number system, binary arithmetic, sign number system, logic gates, that was in unit number 1. We are moving towards unit number 2, which is Boolean algebra, and consists of, after Boolean algebra, we will be studying about the K-maps, the Q methods, how that is all the minimization techniques related to the digital systems. So let us start the Boolean algebra. So before starting Boolean algebra, we need to know what is a Boolean algebra. Now, Boolean algebra is the mathematics of a digital system. That is the mathematics of a digital system. It is used for analysis of the logic functions. That is, any complex or the simple logic functions can be analyzed using the Boolean algebra. In the case of a Boolean algebra, there is a variable and the complement of a variable. That is, suppose we are having A, we can also have A complement. That is, the variable is A, we can have the complement of the variable, that is A bar. Now, Boolean algebra is a system of mathematical logic. Any complex logic statement can be expressed by a Boolean function. The Boolean algebra is governed by certain well-developed rules and laws. These rules and laws are very important, and we will be studying all these rules and the laws in the later slides. In the applications of the Boolean algebra, here we will be presenting in capital letters. That is, in our lectures, we will be writing all the variables in capital letters to represent the variables. Any single variable or a function of the variable can have a value of either 0 or 1. The binary digits 0 and 1 are used to represent the two voltage levels that occur within the digital logic circuit. Here we will be following the positive logic. That is, binary 1 represents the higher of the two voltage level, that is plus 5 volts, and the binary 0 represents the lower of the two voltage level, that is the 0 volt. Ideally, no other voltage can ever occur at the inputs or the outputs. In actual practice, however, any voltage above some value, suppose 2 volt, for example, is treated as logic 1. That is, logic 1 means it can be also treated as true or on or high, or a voltage below some level, suppose 0.8 volt, for example, is treated as logic 0. Logic 0 means also false or off or low. Now, this was in short the what is a Boolean algebra and what are the functions of the Boolean algebra. Next, moving to the next slide, we will be seeing what are the differences between the Boolean algebra and the ordinary algebra. Next, see the first point. In the Boolean algebra, we can write a plus a is equal to capital A. That and a in dot of a is equal to a. But what we are writing in ordinary algebra, a plus a is equal to 2a and a dot a will be a square. Now, in Boolean algebra, 1 plus 1 is equal to 1. That is, we are having some binary addition. And in ordinary algebra, 1 plus 1 will be equal to 2. In Boolean algebra, if a is equal to 1, then if a is equal to 1, then a will be not equal to 0. Similarly, if a is equal to 0, then a will be not equal to 1. These are all the conditions of the Boolean algebra and the ordinary algebra. Now, what we can see that in the case of a Boolean algebra, there are many differences between the Boolean algebra and the ordinary algebra and the binary number system. Here in Boolean algebra, the variable a has a logical value. That is, it does not have any numerical significance. In Boolean algebra, there is nothing like subtraction or division in the Boolean algebra. Also, there is no negative or fractional numbers in Boolean algebra. In Boolean algebra, the multiplication and the addition of the variables and the functions are also very logical. They actually represent some logical operations. Logical multiplication is same as the AND operation and logical addition is same as the OR operation. There are only two constants, 0 and 1 within the Boolean system, whereas in ordinary system, that is an ordinary algebra system, we can have only any number of constants. A variable or a function of variables in Boolean algebra can assume only two values, either a 0 or 1, whereas the variables or the functions in ordinary algebra can assume an infinite number of values. And another important point is any functional relation in Boolean algebra can be proved by a method of perfect induction. Perfect induction is a method of proof where a function relation is verified for every possible combination of values that the variables may assume. This can be done by forming a truth table. A truth table, already you know the truth table. In the case of a logic gates, you have seen the truth table. Now, a truth table shows how a logic circuit responds to various combinations of logic levels at its inputs. This was the differences between the Boolean algebra and the ordinary algebra. Now moving to the next slide, that is the history of the Boolean algebra. The Boolean algebra was invented in the year 1854 by an English mathematician. That is, who was the English mathematician? George Boole. From his name only, the Boolean algebra term came into effect. Now the mathematician George Boole invented a new kind of algebra, the algebra of logic in the year, it was invented in the year 1854, which was also known as the switching algebra or the Boolean algebra. He stated that symbols can be used to represent the structure of logical thought. Boolean algebra differs significantly from the conventional algebra. We know this from the previous slides. This algebra deals with the rules by which the logical operations are carried out. Here, the digital circuit is represented by a set of input and the output symbols, and the circuit function expressed as a set of Boolean relationships between the symbols. Next is the logic operations in the case of a Boolean algebra. First one is AND operation, OR operation, and the complement operation. Now see this AND operation. The AND, OR, and the NOT are the three basic operations or functions that are performed in a Boolean algebra. In addition, there are some derived operations such as the NAND, NOR, XOR, and XNOR. These things already, these are the basic gates or the universal gates and the exclusive gates. Already you have studied in the previous lectures. These operations have been described in the previous lectures. If you have not studied, then you can go through the previous lectures. That is lecture number 11, 12. All the gates are explained there. Now moving back to the AND operation. The AND operation in Boolean algebra is similar to the multiplication in ordinary algebra. In fact, it is a logical multiplication as performed by the AND gate. Next is the OR operation. The OR operation in Boolean algebra is similar to addition in ordinary algebra. In fact, it is the logical addition as performed by the OR gate. Next is the complement operation or the NOT operation. The NOT operation in the Boolean algebra is nothing but the complementation or the inversion. That is the negation as performed by the NOT gate. The NOT operation is indicated by bar over the variable. This bar signifies that this is the complement operation. This was in short the logical operations of the Boolean algebra. Next are the postulates of the Boolean algebra. The axioms or the postulates of the Boolean algebra are a set of the logical expressions that we accept without proof and upon which we can build a set of the useful theorems or the laws. Actually, axioms are nothing more than the definitions of the three basic logic operations. Already we have told you. What are the basic operations? They are the OR, and the invert operations. Each axiom can be interpreted as the outcome of the operation performed by the logic gate. Now, see this axiom 1. Axiom 1 is 0.0 is equal to 0. This is nothing but AND gate. Next is axiom 2. 0.1 is equal to 0. Axiom 3 is 1.0 is equal to 0. Axiom 4 is 1.1 is equal to 1. Now this 4, these are the based on the, this 4 are based on the, this 4 are based on the AND logical operation of the Boolean algebra, which indicates the multiplication. Next is axiom number 5. Axiom number 5 is 0 plus 0 is equal to 0. Axiom number 6 is 0 plus 1 is equal to 1. Axiom 7 is 1 plus 0 is equal to 1. And axiom number 8 is 1 plus 1 is equal to 1. Now axiom number 5, 6, 7 and 8, all these are the implementations of the OR operation in the case of the Boolean algebra. Next is axiom number 9. 1 bar is equal to 0. Similarly, axiom number 10 is 0 bar is equal to 1. Now, axiom number 9 and 10 are the implementations of the invert logic operation or the complement logic operation in the case of the Boolean algebra. Next, coming back to the laws of the Boolean algebra. Now we will be learning about the various laws of the Boolean algebra. First one is the complementation laws. These laws means, the term complement means to invert, that is to change zeros to ones and ones to zeros. The 5 laws of the complementation are as follows. Law number 1 is 0 bar is equal to 1. Law number 2 is 1 bar is equal to 0. So law number 3 is if a is equal to 0, then a bar will be equal to 1. Law number 4, if a is equal to 1, then a bar will be equal to 0. Next is law number 5, which is a very important law. A double bar will be equal to a. So this were the complementation laws. Next are the AND laws, which comes under the laws of the Boolean algebra. In the case of the AND laws, there are 4 AND laws. The 4 AND laws are as follows. Law number 1 is a dot 0 is equal to 0. Law number 2 is a dot 1 is equal to a. Law number 3 is a dot a is equal to a. And law number 4 is a dot a bar is equal to 0. These are the 4 laws of the AND laws. Next are the OR laws. The OR laws comes under the laws of the Boolean algebra. In the case of the OR laws, there are also 4 OR laws. Law number 1 is a plus 0 is equal to a. Law number 2 is a plus 1 is equal to 1. Law number 3 is a plus a is equal to a. Law number 4 is a plus a bar is equal to 1. Remember one thing, that the laws of the Boolean algebra are very important in the due course of the digital electronics course, because you have to remember each and every laws, and these laws are also very important for the minimization techniques. Next are the commutative laws. The commutative laws also comes under the laws of the Boolean algebra. Now in the commutative laws allows changing position of the AND or the odd variables. There are 2 commutative laws. This is the first law. Law number 1 is a plus b equal to b plus a. This law states that a or b is the same as b or a. That is, the order in which the variables are ORed is immaterial. That is, this means it makes no difference which input of an OR gate is connected to A and which is connected to B. Now we will prove this law by the truth table illustration. Now this is the A plus B. This one first input is A, second input is B. This one the output is, and this is the OR gate. So the output is A plus B. This one is equal to, see this one, B is the first input, second input is A, and the output is B plus A. We have to prove this too. How we will be proving it? We will be having the truth table. Now let us see the truth table. This is A and B, and the output is A plus B. Similarly, in this diagram, this is B and this is A. Why? Because B is the first input and the A is the second input, and the output is B plus A. So the combinations are 0, 0. In the case of 0, 0, what is the addition? This is 0. 0, 1 is 1. 1, 0 is 1. And 1, 1 is 1. Similarly, in this combinations, this is in first input is B, second input is A. So this is 0, 0. The output is 0. 0, 1, the output is 1. 1, 0, the output is 1. And the 1, 1, the output is 0. Now see these two things, this one and this one, the outputs of the two truth tables are same. So from here what we can say that? We can say that this law is proved, that is a plus b will be equal to b plus a, and we have proved it from the truth table. By making the truth tables, we can see that the outputs, that is output, first output is a plus b and the second output is b plus a. Both of these output combinations are, all of these are equal, that is first is 0, second is 1, third is 1 and the fourth is 1. Similarly here also the first is 1, sorry, the first is 0, second one is 1 and third one is 1 and the fourth one is 1. This and this combinations are both same. So we can say that this law 1 is proved. Now let us go to the second law. Now before moving to the second law, this commutative law, this law can be extended to a number of variables. The law was, what was the law? The law number 1 was a plus b was equal to b plus a. Now this law can be extended to any number of variables. Now this we are taking as example, that is a plus b plus c, that is a plus b plus c will be equal to b plus c plus a, will be equal to c plus a plus b, will be equal to b plus a plus c. That is, we are just changing the positions of the variables. C moves here, if it moves here also, all the outputs will be same. Next is law number 2. Law number 2 is a dot b will be equal to b dot a. This law states that a and b is same as b and a. That is, the order in which the variables are ANDed is immaterial. This means that it makes no difference which input of an AND gate is connected to A and which to B. The truth table illustration is given here. These are the truth table illustrations to prove this law. Now we will be seeing how we are proving it by the truth table illustration. Now see, this one is the first AND gate we are using. Here the first input is A and the second input is B. So the output is A dot of B. Next is this case. Here the first input is B and the second input is A, and this one the output is B dot A. So just we will be seeing the truth table combinations and the corresponding outputs. Now see here, A and B is here as the two inputs and A dot B is the output. So just look here, 0 0 the output is 0, 0 and 1 the output is 0, 1 0 the output is 0, 1 1 the output is 1, because we are just doing the multiplication. So the combinations of the outputs are 0 0 0 and 1. Now look in the second truth table. Here the first input is B and the second input is A and the output is B dot A. Now see the combinations, 0 and 0 the output is 0. Just the multiplication. Next is 0 and 1 the output is 0. Next is 1 and 0 the output is 0. Next is 1 and 1 the output is 1. So we can see that, so what we can see that this one, again this truth table, the output combinations of this truth table and this truth table are both are same. So we can say that this law is proved, that is A dot B will be equal to B dot A. So it is proved. Next, in the case of the commutative laws, which falls under the laws of Boolean algebra, is that this law can be extended to any number of variables, such as A dot B dot C is equal to B dot C dot A is equal to C dot A dot B equal to B dot A dot C, which is an extension of law number 2, which was A dot B equal to B dot A. And the proof we have already done in the previous slide. Now next, moving to the next law is the associative law, which falls under the laws of the Boolean algebra. Now, the associative law states that the associative law allows grouping of the variables. There are two associative laws. Laws number one is a plus b brackets plus of c is equal to a plus within bracket b plus c. This is law number one, that is in brackets a plus b plus of c is equal to a plus within brackets b plus of c. Now this means that a or ORed b ORed with c is same as a ORed with b or c. This law states that the way the variables are grouped and ORed is immaterial. The truth table gives next will illustrate the law. We will be proving the law by the truth table illustration. So just we have drawn the logic circuit, that is these two are the OR gates, that is this one is the first OR gate where there are two inputs. First one is A and B, so the output is A plus of B, and here this C is coming, this is again OR, so this is A plus of B within brackets plus of C. So this is the first truth table of this one, of this logic circuit, where the expression is in brackets a plus b plus of c. So just see here, we are taking three variables a, b and c, and the other output is a plus b and the other output is a plus b plus of c. So take the first case, 0 0 0, output is 0, again the output here is 0, 0 0 0 1, the output is 0 and here the output is 1, 0 1 0, output is 1 and here also the output is 1, 0 1 1, the output in case of a plus b is 1 and in the case of a plus b plus c is also 1. Next case is 1 0 0. In the case of 1 0 0, the output is of a plus b is 1 and the output in the case of a plus b in brackets plus of c is 1. Next case is 1 0 and 0. First output is 1 and the second output is also 1. Similarly, the next combination is 1 1 0. The first output is 1 and the second output is 1. In the last combination, that is 1 1 1, the first output of a plus b is 1 and the second output, that is of in brackets a plus b plus of c is 1. Now moving on to this expression, this is a plus of in brackets b plus c. So first we will take b plus c. This one is b and c and this is the OR gate, so the output is b plus c, and with b plus c we will be doing OR of a, that is plus of a. So b plus c is one output, sorry, is one input and a is one input to the second OR gate. The output is a plus in brackets b plus of c. Now we will be doing the truth table illustration of this expression, that is this logic diagram. So a, b and c is there, which are the three inputs. B plus c is one output, again a plus in brackets b plus c is the other output, that is there are two outputs. First case C 0 0 0, the outputs are 0 and 0. Next is 0 0 1, the outputs is 1 and 1. Next is 0 1 0, the output are 1 and again 1. Next is 0 1 1, the output is 1 again and the other output is also 1. Next case is 1 0 0, the output in case of b plus c is 0, in case of a plus of brackets b plus c is 1. Next case is 1 0 1, the output is 1 and the other output is also 1. Next case is 1 1 0, the output is 1 and here also the output is 1. Last case or the last combination is 1 1 1, the output in case of b plus c is 1, in the case of a plus in brackets b plus c is 1. Now look at this two tables, this table and this table. all the values are same. So what we can say, that this expression is equal to this expression. This is proved. So law number 1 is proved. By the illustration of the truth table, we have proved this one. Now again, this law can be extended to a number of variables. How? We will be seeing it in the next slide. Now, this associative law, that is a law of first law, a plus b in brackets plus of c is equal to a plus in brackets b plus c, can be extended to a number of variables. How? We are showing it. That is a plus in brackets b plus c plus d. We have included a new variable, that is d is equal to a plus b plus c in brackets plus of d. Next is equal to brackets a plus b, within bracket is a plus b, plus of bracket is within bracket c plus d. So all these are same. That is just, we have, as we have already told it, that it allows grouping of variables. We are doing some groups. Next is the law number 2, that is a dot b into c is equal to a into b dot c. Again, let me read. Law number 2 is a dot b in brackets into c is equal to a into in brackets b dot c. Now this is the law 2 in the case of the associative laws, which falls under the laws of the Boolean algebra. Now again, how we can say it, that a and b ended with c is same as a ended with b and c. This law states that the way of the variables are grouped and ended is immaterial. Now this has to be proved by using the truth table or the illustration of the truth table. Here again, see this one a dot b. So we will be using an AND gate. So a and b are the two inputs and the output is a dot of b. This and this will be again an AND. That is ab is one input and c is the other input. This one is an AND gate, so the output is A and B ANDed with C. Next is this one, this expression, that is A ANDed with B and C. So B and C are the two inputs and this is one AND gate, so the output is B, C. Next, this one is the one AND gate and the input is BC and the other input is A. So the output is A into B and C. So next we will be doing the illustrations of the truth tables. Next is A, B and C are the three inputs. Similarly here A, B, C are the three inputs and the one output is A, B and the other output is A, B, A and B ended with C, and one output is BC in the second truth table and the other output is A ended with B and C. Now see the first case or the first truth table and the first case of the first combination 0 0 0. The first output is 0 and this one is also 0. Next is 0 0 1. We are just doing the multiplication. So 0 and 0. Next is 0 1 0. Next here the output is 0 and other output is 0. Next is 0 1 1. This is 0 and 0. Next is 1 0 0. That is 0 and 0. Next is 0 1 0 1. So it is 0 and 0. Next is 1 1 0. So the output is 1 and 0. Next is 1 1 1. The output in case of AB is 1. In the case of A and B ended with C is 1. So you have to consider this truth table, this particular combination of this A and B ended with C. Now look here in the next truth table, that is A, where the three inputs are A, B and C and the outputs are B dot C and A ended with B and C. Now the first combination output is 0 and 0. Second one is 0 and 0. Next also 0 and 0. Next one is 1 and 0. Next again 0 and 0. Next is 0 and 0. Again 0, 0 and 1 and 1. Now we will consider this one. Which one? This table. So you can see this and this one and this one, both the combinations, that is all the cases in all the combinations, in the 8 combinations, both all the output values are same. There are 8 combinations from 0 to 7. Here also there are 8 combinations 0 to 7, and all the combinations outputs values are same. Here also it is same, this is also same. So what we can say, that this law is proved, that is A and B ANDed with C is equal to A ANDed with D and C. So this is proved. Now again, this law can be extended. This law can be extended again, this associative law can be extended to a number of variables. Now if we include a variable here, that is A, that is D, suppose. Now for example, suppose I am saying A ANDed with B, C, B and C and D will be equal to A and B and C ANDed with D equal to A and B ANDed with C and D. So all of this are same, and this is the extension of the associative law, which is the second law of the associative law. Next is the distributive law, which falls under the laws of the Boolean algebra. Now what does the distributive law suggest? The distributive law allows factoring or multiplying out of the expressions. There are 3 distributive laws. This is the first law, that is A into B plus C will be equal to AB plus of AC. So this law states that ORing of several variables and ANDing the result with a single variable is equivalent to the ANDing that single variable with each of the several variables and then ORing the product. The truth table illustration is given here, and we will be proving it if this and this both are true or equal. Now just look here in this one. This is A into B plus of C. So first we will be drawing this circuit, that is B plus of C. B and C are the 2 inputs, and it is going inside a OR gate, and the output is B plus of C. Now B plus C dot of A. So B plus C is coming here, and another input is A. These are going to a OR gate. These are the 2 inputs of an OR gate, and the output is A into B plus of C. Now consider this one. This one is A dot of B plus of A dot of C. So here first take this one, that is A dot of B. So this is the AND gate. This one is A and B, and the output is A dot B. Next is A dot of C. Now this one is the AND gate. So this one is A and C, and this one is A dot of C. Now these 2 are going to a OR gate. Why? Because there is a plus sign in between them. So AB and AC. This is going to a OR gate. From the OR gate, the output is AB plus of AC. Now we will be seeing the truth table illustration and how we are proving it. Now this is A, B and C are the 3 inputs. First output is B plus C, and the second output is A into B plus C. Now first combination is 0, 0, 0. The 2 outputs are 0 and 0. Next combination is 0, 0, 1. The 2 outputs are 1 and 0. The next combination is 0, 1, 0. The 2 outputs are again 1 and 0. Next combination is 0, 1, 1. The output combinations are 1 and 0. Next is 1, 0, 0. The output combinations are 0 and 0. Next is 1, 0, 1. The output combinations are 1 and 1. Next is 1, 1, 0. The output combinations are 1 and 1. Similarly, 1, 1, 1. The output combinations are 1 and 1. Now consider this one. This one. That's why I have selected this one. We will be considering the values of A dot of B plus of C. That is A into B plus of C. Next, consider this logic diagram and the corresponding inputs and the outputs. Next is A, B and C are the three inputs and there are three outputs, AB, AC and AB plus of AC. So 0, 0, 0, this one is 0, 0 and 0. 0, 0, 1, this one is 0, 0 and 0. 0, 1, 0, that is 0, 0, 0. Next is 0, 1, 1, this is 0, 0 and 0. Next is 1, 0, 0, so it is 0, 0 and 0. Next is 1, 0, 1, so it is 0, 1 and 1. Next is 1, 1, 0, this one is 1, 0, 1. Last one is 1, 1, 1, so it is 1, 1 and 1. Again, we will be considering this one. So, just we are selecting this one. Now, after selecting, what we can see that A into B plus C and AB plus of AC both are having the same results. That is, each one of the combination outputs are equal. That is 0, 0, 0, 0, 0, then 1, 1, 1. Similarly, here also it is 0, 0, 0, 0, 0, 1, 1 and 1. So, what we can say that this law is proved. That is A into B plus of C is equal to A dot B plus of A dot C. So, this one is proved. Now, the distributive law can be applied to single variables as well as combinations of the variables. That is, it can be extended to any number of variables such as A into B into C into D plus of E will be equal to A, B, C, D plus of A, B, C, E. Next is A, B into C, D plus of E, F, which is inside the brackets. So, it will be equal to A, B, C, D plus of A, B, E on F. Next is the distributive law. That is the second law. Now, the previous slide, what we can say that in the previous slide, suppose, for example, if we are taking the distributive properties often used in the reverse, that is, suppose if it is given AB plus of AC, we can replace it by A into B plus of C, and AB C plus of ABD can be replaced as AB into C plus of D. We can replace it like this. So, moving back to the second law. The second law states that A plus of B into C will be equal to A plus of B, which is inside the brackets, into A plus of C, again inside the brackets. So, this law states that the ending means the AND gate, that's ending of the several variables, and the ORing, the result with the single variable is equivalent to the ORing that single variable with each of the several variables, and then ending the sums. This can be proved algebraically. Here this proof is done algebraically. That is, we are using the Boolean algebra to prove it. And also you can do it with the truth table. Both are correct. If you are doing with algebra method, that is, if you are using the Boolean algebra method or the truth table method, both are correct. But I would suggest that you should be doing the Boolean algebra method because it is more simpler. But for your proper understanding, here I have used both the methods. First of all, we were using the truth table illustration to make you understand. And after you have understood, you can use the Boolean algebra methods. Now let us see the proof of this law number 2. So taking the RHS means right hand side is equal to A plus of B into A plus of C, which both of these are inside the brackets. So just we are multiplying it. This one is this one, that is A into A plus of A into C. Next is B into A plus of B C. Again say it, A into A, this is A dot A. Next is A dot C, this one. Next is B dot A, this one. And next is B dot C, that is this one. So we are having 4 terms. So A dot A means it will be A. Already I have told you in the previous slides. In the previous exams also we have proved that we have seen that A dot A is equal to A plus of AC plus of AB. Just I've changed the positions. From BA I can write AB plus of BC. From here I have taken A as the common. So A into 1 plus of C plus of B plus of BC. Now see here, if we consider C plus B as one variable, we can write A plus this one C is equal to 1. Again 1 plus B will be equal to 1. So this one is, the whole one will be equal to 1. So you can write A dot 1 plus of BC. So you can, after A dot 1 is equal to A, so A plus of BC. So this one is proved. Which one is equal to left hand side? So this one is A plus of BC. So we can prove that A plus of B into A plus of C. Already we have proved that it is equal to A plus of BC. Next, we will be proving this using the truth table illustration. Now, how to prove it? Now, this one is one term, that is B into C. So, it will be going inside a AND gate. This is B and this is C and B. This is going inside a AND gate. So, the output is B and C. This B and C is coming to the OR gate and A is coming as the input. So, the output is A plus of B into C. Next is this one, A plus of B into A plus of C. This one is A and B. This one is the OR gate, so it is A plus of B. Next is A plus of C. This is A and C. Again, this one is the OR gate, so the output is A plus of C. Both of these are going as the inputs to the AND gate. Why? Because inside between them there is a dot. Here there is a dot, that is multiplying. So you will be using a AND gate. That is A plus of B into A plus of C. Now, both of these logic diagrams we will be applying in the truth table. So, A, B and C are the inputs and BC and A plus of BC are the two outputs. So, just look here, 0, 0, 0, the outputs are 0 and 0. Next is 0, 0, 1, the outputs are 0 and 0. Next is 0, 1, 0, the outputs are 0 and 0. Next is 0, 1, 1, the outputs are 1 and 1. Next is 1, 0, 0, the outputs are 0 and 1. Next is 1, 0, 1, the outputs are 0 and 1. Next is 1, 1, 0, the outputs are 0 and 1. Next is 1, 1, 1, the outputs are 1 and 1. Now consider this one, that is this one. This one, I've selected this one as I will need it in the second step. Next is this one, A, B and C, and the outputs are A plus B, A plus C. Which one will be acting as the, this one, these two will be again acting as the inputs, and the last output is A plus B into A plus of C. So this one is 0, 0, 0, the outputs is 0, 0, and here the ultimate output is 0. Next is 0, 0, 1, the outputs is 0 and 1, and the ultimate output is 0. Next is 0, 1, 0, the outputs are 1 and 0, and the ultimate output is 0. Next is 0, 1, 1, the outputs are 1 and 1, and the last output is 1. 1, 0, 0, the output is 1 and 1, and the last output is 1. Next is 1, 0, 1, the output is 1 and 1, and the last output is 1. Next is 1, 1, 0. The outputs are 1 and the last output is 1. Next is 1, 1, 1. The two outputs are 1 and the last ultimate output is 1. So again consider this one and make it is a select this one. So you see that values of this one and this one, that is a plus of bc and a plus of b into a plus of c, both are same, that is 0, 0, 0, 1, 1, 1, 1 and 1. Again see here 0, 0, 0, 1, 1, 1, 1 and 1. So you can say that a plus of bc will be equal to a plus of b into a plus of c. This is proved by the truth table illustration. So we can see from here that the second law of the distributive law is being proved by the truth table representation or the truth table illustration. So we have come to the end of the lecture and I am very thankful to all of you. Thank you.